The major problem solving, or rather, the major equation solving strategy you know so far is isolate and undo. So each of these equations is structurally sort of identical. We've got x that's buried inside some other function and some other stuff happening. And so what we need to do to isolate x, because at the end of each of these we want to say like x equals something, is we have to isolate the entire term that contains x so that we can undo whatever function x is inside of. So here x is inside of 2 to the something, here it's inside of root, here it's inside of sine. So in each of these cases, we isolate the term by adding 7. And now that each term is isolated, we can apply the inverse function to both sides to undo it. So the inverse of 2 to the power of something is log base 2. The inverse of square root is squaring, and the inverse of sine is arcsine. So here I applied log base 2 to both sides, and these undo each other, so we've got 5x minus 1 equals this thing. This is just a number. Log base 2 of 7 is some number. It's whatever power of 2 equals 7. If you want to, we could define this to be k, because that's sort of easier to look at, and so now we can solve for x to the rest of the way. We can add 1 to both sides, and we can say that x equals k plus 1 over 5, and then you can substitute back in for k. You could say it is log base 2 of 7 plus 1 over 5, and that would be a really great solution. Here, similar idea. You know how to solve for x here. Here, I just wanted to put this example in to encourage you not to blindly do things. You know that it's impossible for the output of a sine function to be larger than 1. So right away, we can stop and conclude that there are no solutions to this equation. So you always want to be thinking when you're using algebra. Don't just mindlessly apply what you can apply. So what about a problem like this? I've got a root and another root and a number. The number one way to misunderstand how to solve this would be thinking, okay, I'm going to square both sides to undo. This is not algebraically legal. You can't square an expression with 2 terms and square each of the terms separately. And you know this already when you're not being tempted into it. If I asked you what is a plus b squared, you know none of you would write a squared plus b squared because you know that that's not what you do. What this means is that you're multiplying each of the things by all the other things. So it would be a plus b times a plus b. So the a's multiply the ab, the ba, and the b. However, I think it's very, very tempting when you see a square root. You really want to simplify those square roots, and so you think, oh, I'm just gonna apply the squared to each one of those and undo them. So don't get seduced by the algebra. Remember what is actually true and right and just and good. So you're probably not feeling so good now because I seem to be telling you to expand this thing, and you could expand this thing, and it's probably good practice to do so. But let's be a little bit more strategic. You know that you can reorganize an expression, so you don't just have to expand this entire thing and simplify. Instead, let's consider if we'd reorganized a little bit. So what if we moved the 1 to this side and we moved this term to that side? So we'd have 1 minus x plus 1 equals 2x plus 4. Algebraically equivalent, but now if we square both sides, it's a little bit nicer because this side, the squaring actually does undo the square root. And so we get 2x plus 4 right away. This side, you still have to expand the long way, but at least that's a little bit better. So if we were to expand this, some of it would simplify, but you'd still have a root equation. And then what we'd want to do is move everything that's not the root over to the other side. So we'd have root equals stuff, and then you'd square it one more time so that you can solve the rest of the way. So that's why I said this is a 2-step strategy. You want to isolate one of the roots so that you can undo it. That's going to give you another root somewhere, so then do the whole thing over again. Isolate that root and square it to undo it. Let's see what it looks like. So I have this term squared, so I've written the root plus 1 times the root plus 1. I've chosen to write little blobs here instead of writing the 1 minus x because I know it's like I'm defining a variable called blob, and the blob variable equals 1 minus x. And I'm just doing it because it's faster to write. So if I've got root times itself, that just gives me blob because the roots undo each other when you square them. Then I've got 1 times the root plus another 1 times the root. So that gives me 2 times root blob and then plus 1. Okay, so now let's substitute back in for blob. So my blob was 1 minus x. I'm going to keep the blob inside the root here. So now I want to isolate this by moving everything else to the other side. So 2 root blob equals. So let's subtract 1 and subtract another 1. So that's taken care of and that's taken care of. And so 4 minus 2 is 2. Let's add this x to both sides. So that gives me 3x. And now I'm in a nice position to square both sides again. So on this side, I've got 9x squared plus 6x plus another 6x is 12x plus 4. On this side, I've got 4 times the quantity blob. And what was blob? Blob was 1 minus x. So that's 4, whoops. So that's 4 minus 4x equals this other stuff. All right, so if I add 4x to both sides, so now I'm noticing this is a quadratic equation, and we've got a lot of tools for solving quadratics, so I'm going to write it in standard form by moving everything over here. So I'll add 4x to both sides, so that gives me 16x here, 9x squared. I'm going to subtract 4 from both sides, and so that gives me 0. So now I notice this has come out very nicely. I can factor an x out here, so I've got x times 9x plus 16. And so I know that either x is 0 or x is whatever we get when we solve this one for 0. So 16 equals 0, so it's like negative 16 over 9. Okay, but I shouldn't just write a box around my equations because you actually need to verify that both of these are in the domain of the original function up here. So let's double check 0. If I plug in 0, I've got just the square root of 1, so that's 1, minus the square root of 4, which is 2. So 1 minus 2 is negative 1. So 0 seems to check out. Let's look at this other one. So if I plug this back in up here, I've got 1 minus 16 ninths. So that's like 1 plus 16 ninths. So 1 plus 16 ninths, 1 is the same as 9 over 9. So that's like that. And then if I combine those two, 9 plus 16 is 25 over 9. So that simplifies to be root 25 on the top, which is 5, divided by root 9 on the bottom, which is 3. So that simplifies to be 5/3. Okay, so what about this other one? I've got 2 times negative 16 over 9 plus 4. So that gives me, what's that? Negative 32 ninths plus 4. Let's rewrite this under the same denominator. So 4 times 9 is 36 ninths. So that gives me 36 minus 32 is 4 ninths. So that gives me 2/3. So 5/3 minus 2/3 equals 3/3, which is 1. But 1 is not the same thing as negative 1. So that's what's called an extraneous solution, because the signs got lost in the process of squaring, and so this is not a solution to the original equation. So that's the last step you have to do just to be sure, is you have to plug back in to make sure it actually satisfies your original equation.